So today we're going to take a look at the beginning of chapter 6, which is on trigonometry. And the first thing I like to kind of do is just write down the word, take a look at it, and see if we can figure out what does that word really mean. So trigonometry. Best way to kind of figure out what it means is to break it down as much as you can, maybe into like a prefix or a suffix, something that you recognize. Is there anything in that word that anybody recognizes yet?
Try.
Okay. What's that mean? Yeah, it means 3. So something to do with 3. Yeah.
Metry means measurement.
Yeah, metry means measurement. Anything else there that you see? You see it in math, in geometry quite a bit. This part, yeah.
For gone like a triangle or something.
So gone. It's a lot of times, and it's at the end of the word. And this word, it's in the middle.
Like polygon or something.
Right. What does it mean? In that
Sides.
case? Yeah, sides. Yeah.
3-sided numbers.
So if you literally break that word down, it's 3-sided measurement. So in other words, we're measuring a shape that has 3 sides, okay? Triangles. So we don't normally call triangles trigons, but you can. We use the word gon for other shapes, hexagon, octagon, pentagon. 4-sided shape, we usually use the word quadrilateral, but you can also call it a tetragon. Okay? So trigon is just another name for a triangle. All right, so here's an example of something that we could do in trig that would involve a triangle. So let's say that we had like a fire somewhere. Right, so there's a fire. Okay, let's say in a forest, and there are towers. Like if you've ever hiked Mount Wachusett, you see one up there. There's a tower, and up in that tower, there's usually something like sometimes it's like a big disc, and there's like a sight on it, and they can take the disc and they can turn it, and then they can look at something, and the tool tells them exactly the direction they're looking. So they can say, all right, there's smoke, and they get the compass heading, so they know the exact direction to the smoke. What they don't know is how far away the smoke is. Not a telescope. Maybe it's some kind of scope. I think of a telescope when I'm looking up into the sky, but I don't know exactly what it's called. It could be.
Where is this?
There's one on Mount Wachusett, but it's like a fire tower. Yeah, just at the top of the fire tower. It's inside the tower. But the difficult part is like how far away it is. Okay, they may be able to estimate. It looks like it's 15 miles, 20 miles, but it's hard to tell exactly. So there was a tower here. What it can do is basically get a direction to where the smoke is coming from. In order to figure out exactly where it is, like let's say maybe someday they have planes they can program, put in the exact coordinates, and then the plane can just dump water automatically, without a pilot in it. Well, then they need an exact coordinate to do that. So if there's another tower over here, this tower can say, well, I don't know how far away it is, but I can tell you that it's in this direction. And the idea is that each tower is looking at the fire from a different perspective, and they each have a direction to the fire. What that means is they have an angle here and then another angle over here. So knowing these two angles, which would be the direction that they're looking at to the fire, and knowing how far apart the two towers are, that's easy. It's just like finding the distance between two cities on a map. Okay, the towers are in known spots. We can find anything we want in this triangle right here. We can figure out the distance to the fire from the tower. We can get the angle up here. We can get anything. And if we can figure out the length of the sides in the triangle, then we can pinpoint exactly where the fire is. The key is you need two observers looking at the same thing. Right? That's basically called triangulation. So that's one thing you can do with trig. You can triangulate where someone or something is, as long as two different people can see the same thing. Another example of that is like GPS. Okay, that's triangulation. So it has, if you just have a single satellite, you can't pinpoint where you are. But if you have multiple satellites and they're each seeing you from different spots, the satellites know where they are relative to each other. They can talk to each other and say, I'm here, you're here. And then they can figure out where you are working together. It's a little different because that's 3D.
It's a special kind of compass.
Yeah. Okay, it's a little different with that because it's 3D, but it's still the same idea. GPS is just triangulating where you are. All right, so lots of practical things that we can do in trig. Okay, more so than some of the algebra stuff we've done. Okay, that gets a little bit theoretical sometimes, but a lot of trig we can relate to like applications. Not everything. There are some theoretical things in trig as well. Okay, but that's just one example. Right. So, any question on kind of the idea of what the word trigonometry means? Yeah.
Kind of a little bit far off there, but do you know of any uses for this in space or anything like that? For planet stuff or galaxy stuff or anything like that? Astronomy? Off the top of your head.
Well, I'd have to think more about specific applications to space.
As in, like, the exact area or the exact distance that our planet is away from another star, or another
Yeah, I'm sure
planet,
you could
or-
measure distances. The key is you'd have to be observing something from two different points, so I just have to think a little more about that. But I'm sure there are some other applications for space.
The way they do that
Yeah.
is one, like you take a measurement the whole entire year, and then 6 months later, when we're on the other side of the sun. That's really good.
Yeah, you can take different measurements at different points in time, and then you know how far the Earth was moved in that amount of time because we know the orbit, things like that.
So if you take measurements of looking at the
So before we even really get into triangles or calculating the length of sides, that particular problem would be what's called a law of sines or law of cosines problem. Okay, that's going to be a little later in chapter 7. We just need to understand like the basic parts of a triangle first. And the first thing we're going to talk about is what is an angle. So in a triangle, there are 3 angles. Okay, and each angle in a triangle is made up of line segments. So when you talk about an angle in a polygon, the 2 sides of the angle are made up of line segments. When you talk about an angle drawn by itself, that's not a polygon, just an angle. We usually don't call these line segments.
rays.
Those are rays. Okay, so there's really 2 ways you can draw an angle. By itself or in a polygon. If you draw it by itself, those are rays. And where the 2 rays start from, that is called the vertex. In a triangle, these 3 points are also called vertices. The only difference is the sides of the angle are line segments, they're not rays. When you draw an angle, there's always 2 rays. Okay? One of the rays we call the initial side, the other ray we call the terminal side. Which I think I write somewhere. Yeah, right there. So how do we figure out which side is which? If you draw an angle like this, in this case, that's the initial, that's the terminal. So basically put yourself inside the angle and then rotate counterclockwise. Whatever side you would start at, that's the initial, and as you rotate counterclockwise, where you end would be the terminal. So let's say I drew an angle like this. not the best way to draw an angle. This way is much better. That one's almost, it's like it's been rotated. So I'll talk about that in a second. But if you drew an angle like this is the initial. This is the terminal. So if you were inside the two rays, as you rotate counterclockwise, where would you end up? That's the terminal. Where did you start? That's the initial. Any question on that idea? Which side is initial, which side is terminal? It doesn't matter how you draw it. If you do it like that, initial, terminal. As you rotate counterclockwise inside. We're going to have an easier way to tell which side is initial and terminal, because there's a certain way you should always put the initial side. Like if you want to really draw this angle, what you should really do is do it like this. That's how you should draw it. Try to keep that initial side horizontal, and then the terminal side is wherever it ends up. But you want to keep the initial side horizontal and pointing to the right. That's how you should draw it. Just another example. So we really have two different angles here. Okay, we have the angle that's between the rays. That's the interior of the angle. Then we also have the exterior angle, okay, on the outside. Generally, when we talk about angles, we're going to be referring to the angle that is interior, okay, between the two rays. So any question on the idea that there's two different angles here? Together, they would add up to 360 degrees. So if this interior angle is 45, the exterior is 315. Okay. One thing that's going to be important in trig, there's going to be lots of kind of simple calculations that we're going to want to have memorized to be able to do quickly. Especially if you're going to take calculus next year. Okay, Mr. Babb says that's usually one of the things that always kind of slows people down. They'll forget like the simple things in trig. Like if you know something is 45, you should instantly know what would make it add up to 360, 315. So you have to get really good at working with like 45s and 90s, okay, and 30s and 60s. So like if you had something that was 30, 330 would make it add to 360. Right. So hopefully as we go, you'll get kind of used to working with those angles. And when we start doing trig functions, also quickly knowing what's the sine of 30, what's the cosine of 30, what's the tangent of 30. Those are things we're going to probably want to memorize, so we know them right off the top of our head. Okay. So when we have an angle that we don't know, a lot of times we represent anything we don't know as a variable, but in trig, angles always use Greek letters. I'll say most of the time we use Greek letters. So those are all different Greek letters we'll see throughout the year. Does anybody know the name of, start on the left and work our way to the right? What this first Greek letter is? Yeah?
Alpha.
Yep, so it's alpha. How about that next Greek letter? Yeah? It's beta. These are lowercase, by the way. Capital alpha looks like capital A. Capital beta looks like capital B. How about that one? It's kind of like a Y, but the left side has a little more of a, kind of like a hook on it. Yeah?
Gamma.
That's gamma. And how about the circle with a line through the middle? Yeah?
Isn't that theta?
Which one?
Theta.
Theta. Yeah, it's theta. And what about that last one? Looks kind of like a W. It's the perfect place for it to be in this list. Yeah?
Omega.
Omega. Yeah, omega, the end. Right? It's at the end. It's lowercase omega. If you're thinking, I thought omega looked kind of like a horseshoe symbol, well, that's a capital omega. You see that in electricity for resistance.
I always see those movies.
But we don't use that. We stick with those lowercase letters. Generally, when we're dealing with triangles, we may have 3 angles we don't know. Those are the 3 Greek letters we would use. If we have a problem and there's just one angle we don't know, a lot of times we'll use that. Theta. And those are all appropriate, and it's not saying you can't use an English letter for an angle either. You could. We just usually don't. All right, so earlier I kind of alluded there's a certain way you should be drawing an angle. Okay, if you draw it like this, you're just kind of making it more confusing for someone to figure out the initial and terminal side. But if you draw it in standard position, then you can look at it and there's no question which side is which. So for an angle to be in standard position, 2 things have to happen. Okay, 1, vertex at the origin. 2, the initial side should be pointing to the right. It should be on the positive x-axis. That is an angle in standard position. Just like that. Now, based on that definition, what if I did that? Is that standard position? What do you think, Jake?
It's not the origin.
No, the initial side is okay. It's still on the positive x-axis, but the vertex isn't at the origin. So no, that is not standard position. Okay. Also, if I did this, is that standard position?
No.
No. Is the vertex at the origin?
Yes.
Yeah.
Yeah, the vertex is at the origin, and the terminal side is on the y-axis. But the definition doesn't say anything about where the terminal side should be. It's the initial side on the positive x-axis. So that's not standard position. Okay, so if I ask you to sketch a 45-degree angle in standard position, everybody should pretty much look the same. Right? If I gave you like a coordinate axis, there shouldn't really be much of a difference. I mean, it might be a difference how long you draw the side, but as long as you put the arrow on it, then we know it just keeps going. Any question on what standard position means? Okay. So one way that we can measure an angle, which you're probably familiar with, is degrees. It's not the way that you use when you get into more, well, say, higher level math. Okay, there's another unit that we use besides degrees. If you take calculus, degrees is not something you would use. Does anybody know the other unit that you can measure angles in besides degrees? Well, there's a few. But the other one that's really common in math, yes? Radians. So we have to get really good at working in radians. Okay. If we had a, think of like a circle or like an angle that went all the way around, how many degrees in one full rotation? Anybody know? Yeah?
360.
360. Yeah. And we're going to talk more about it, but there are 2 directions that you can measure angles in, especially as you go around like a circle. Okay, let me show you that. Okay, so when you go in a counterclockwise direction, that's measuring a positive angle. Okay, I can't move the initial side. All I can do is move the terminal side, wherever I want to put it. Yeah.
I was just going to ask, how do gradients relate to degrees? Like, how many gradients are in one?
I'm going to show you.
You're gonna?
Yeah, I'll show you. Put it back at 0. Now, if I go in a clockwise direction, it'd be nice if there was like a little arrow here pointing which way I went. That's a negative angle. So when you measure angles using like a coordinate axis on a circle, you can have negative and positive, and you can have more than 360. More than 360 would mean you've gone around more than once.
Is this the number on the bottom?
Yeah, we're going to talk about that number on the bottom. That has to do with radians. And if you put this at a nice spot, you can start to see maybe a connection between degrees and radians. There are 2 pi radians and 360 degrees.
2 pi r squared.
Just 2 pi.
No, as in like the area of a circle is 2 pi r squared.
Yes, the area of a circle is pi r squared.
Pi r squared.
No 2. Yeah. So if I put this over at 180, how many radians do you think would be in 180 degrees? Yeah. How many? Yeah, 1 pi radians. And you'll notice that all of a sudden you move it, you've got decimals, and then all of a sudden it changes to pi for some of them. There are certain angles that we work with quite a bit. Angles that are multiples of 30, 60, and 45, at least on this program. You're going to see it written as a multiple of pi. So we're going to talk about how do you get that? Like if I said convert 225 degrees to radians, how do you do it? Well, I'm going to show you. I think I'm going to show you today. But then most angles, if they're not a multiple of 30 or 45, like 236, we would usually just write it as a decimal. The accuracy depends on what they want in the problem. That is not an exact answer, 4.12. Okay, let's go back here. How about if we had a counterclockwise revolution, so that's positive direction, but only halfway around? How many degrees would that be?
180.
Yeah, that's 180. And if I still went in a counterclockwise direction, so positive, but I only went a quarter of the way around, it would be how much?
90.
90. So angles, as you can kind of see from the 3 we just did and from that little program where I was dragging the angle around, if you go in a counterclockwise direction, your angles are positive. Okay, so counterclockwise, opposite way a clock would go. Same way if you were like loosening, something, loosening a screw. Oh, counterclockwise. Okay, if you were going in a clockwise direction, okay, when we measure angles in a clockwise direction, that's a negative angle. Yeah, it's like you'd be tightening something. Imagine a deli tightening. So those are the 2 main directions. When we start to talk about angles like in a triangle, then negative angles don't really have meaning. We don't talk about negative angles. The only time negative angles can come up is when we're talking about rotation direction on a circle. The negative just tells you it's a different direction. But angles don't have direction in triangles. You just have the angle. There's no direction. Any questions on that? Okay, angles can be larger than 360. And that just means you've made more than 1 revolution. Angles that are larger than 360 can be challenging to work with, especially when you start trying to do trig in your head. So we're going to talk about ways that we can deal with angles that are larger than 360 easily. Okay, for example, if you asked me, what's the cosine of 390? Oops, you got to type it in on the calculator, and I'm going to put it in degrees. Cosine of 390. Well, it's going to be 0.866. Okay, that's the square root of 3 over 2. I'll teach you how you'll know that. 0.866 is the square root of 3 divided by 2. Now, I knew that the cosine of 390 was root 3 over 2. But I didn't think of it as 390. When I did it in my head, I thought of it as 30. Because when you're doing trig, 390 and 30 are exactly the same thing. And I'm going to show you later today how I did that. Okay. Yeah, I minus 360 from it. So when we start to deal with figuring out trig functions, we can add or subtract 360 to an angle. And it doesn't affect when we do trig on it. Trig is like sine, cosine, tangent, secant, cosecant, and cotangent. All right, so these are all little things we're going to learn as we go through trig. I'm just kind of introducing them a little bit as we go. All right, so another term, coterminal. Well, to give you an idea, 390 degrees and 30 degrees are example of coterminal angles. Angles are coterminal if they have the same initial and terminal sides. So let me bring up that program again and just kind of show you. There's 90. Notice where the initial side is and the terminal side. Now I'm going to do 450. How does the initial and terminal side compare now to where they were at for 90? Yeah?
5 times what it was. Because it used to be...
Just the sides, not the angle itself.
The signs?
The sides.
Oh, the side.
How do the sides of the angle now compare to where they were for 90?
They're larger.
No, they're the same size. Yeah. They're in exactly the same place. There's no difference between where the initial and terminal side is here and where it is right there. Exactly the same place. If you can draw angles and those sides can be in the same place, those are coterminal angles. So 90 and 450. What's the connection between those? They're coterminal because you can take one and do what to it to get the other one. You can kind of think of it 2 different ways. Yeah?
Well, 450 minus 90 is 360. Or 450 minus 360 is 90.
Yeah. If you subtract 360 from something, you'll get an angle that's coterminal. Or if you, what else could you do? You could add 360. Yeah. So to find coterminal angles, you can add or subtract 360. And that's what makes trig easier to do in your head. Right? So if you ask me, what's the sine of 405 degrees? Right away, I think 45. I take 405 and I subtract 360 without even thinking about it. And I say, okay, now what's the sine of 45? And that's something I have memorized. It's square root 2 over 2. You're going to get lots of decimals when we start typing these things in. We're not going to want to work with those decimals. We're going to want to learn what those decimals are equivalent to as a fraction. And sine of 45 is square root 2 over 2. Okay, we'll prove that. I'll show you how to do it. All right, so let's try sketching a few angles, and then finding an angle that is coterminal with the one I give you, both a positive coterminal angle and a negative. All right, so 30-degree angle. I'm not looking for exact. I'm just looking, roughly in the right spot. Where should the initial side be, based on what the directions say? Yeah.
On the positive x-axis.
Yep. So we're going to put that on the positive x-axis because it said standard position. And where would 30 degrees be? Yeah.
It'd be in quadrant 1.
Yeah, it'd be in quadrant 1, closer to the x, middle, or closer to the y.
Closer to the x.
Yeah, closer to the x. It'd be 1/3 of the way through the quadrant. So 45 is halfway. Well, just make it look like it's less than half. And now let's find an angle that is coterminal and positive. What is an angle that is coterminal with 30 and positive? Yeah, 390. And an angle that is coterminal, I would never want the negative if I was doing something in my head, but they're asking for it. So what would the negative coterminal be? Yeah?
-330.
Yeah, those are just the first ones. You could add and subtract 360 over and over, keep getting more. Right? But that answers the question. Right, let's try 145. Okay, initial side, positive x-axis. What about the terminal side? Closer to y, right in the middle, or closer to x? Where's 145? Yeah.
Yeah, so because 2 halves is 180.
What's it halfway around is 180?
Yeah.
Yeah,
So
halfway is
right
180.
into quadrant 2, right in the center.
Right in the center?
No.
145 it's more towards the 180. Right in the center would be 135. So this is 10 degrees past center. Not much, but it's just a little bit past the center. Okay, so there's 145. And what would be an angle that's coterminal and positive to 145? Yeah?
505.
Yep. If you take 360 and add 145, you'll get 505. And an angle that's coterminal and negative, just minus 360, and you get negative 215. Okay, how about this one? Initial side is in the same spot. Where's the terminal side going to be?
It's gonna be in quadrant 4
It's going to be in quadrant 4, closer to x, y, or right in the middle.
in the middle.
That's right in the middle. Yep. Any multiple of 45 always has its terminal side right in the middle of the quadrant, which essentially means the slope of it is a 1, or like a negative 1. We don't really think of array as having a slope, but if that idea makes sense, that's what it looks like. Okay, so coterminal and positive. What's an angle that would be the same as negative 45? Yeah.
It would be like positive 310,
Not quite.
315.
315. Yep, this takes a little practice to get good at them. And what about an angle that's coterminal and negative? Negative 405. Yep. Okay, so any questions on sketching angles and identifying them as finding positive and negative coterminal angles? Okay. So, we're going to talk a little bit about definitions based on the sides of angles. And I'm going to represent my angle by theta. Okay, so I have some angle. It's theta degrees. If it was acute, what would that mean about my angle? Yeah?
Less than 90. Right? Less than 90 degrees.
Okay, less than 90 degrees. I can think of an acute angle that's less than 90, or I can think of an angle less than 90, but it's not acute. Yeah? It has to be greater than 0. So when we start getting into these negative angles don't have anything to do with the definitions I'm about to show you. Okay? An acute angle has to be between 0 and 90. So negative 10 is an angle. It's just not considered acute. It's not, according to the definition. Yeah.
What if it was like negative 45?
It's still not considered acute. So acute only applies to angles that are measured in the positive direction. Yeah. Let's do the next one a little different. The next category is between 90 and 180. What kind of angle is between 90? Well, actually, let's say exactly 90. What kind of angle is exactly 90? Yeah, that's a right angle. That's when it's exactly 90. And then the next category is 90 to 180. Bigger than 90, less than 180. Yeah,
Obtuse.
yep, that's obtuse. So all those definitions apply to a single angle. Now we're going to look at a term that applies to a pair, and that's complementary. So, what does it mean if two angles are complementary? Yeah?
Both of them add up to 90 degrees.
They both add up to 90, and they have to be positive. So if you had like a negative 10 and a 100, those add up to 90, but they're not complementary. Okay, complementary angles have to be positive angles that add up to 90. What's another way to say that, based on one of the terms we just had up above? Instead of saying two positive angles that add up to 90, you could just say, you could just say two acute angles, because the word acute, by definition, means positive. Yep. And then the next category applies to a pair that adds up to 180. What do we call that? Yep.
Supplementary.
Supplementary. Yep. Again, same deal there. If you had a 200-degree angle and a negative 20-degree, you may say that adds up to 180. It's not complementary. Negative angles do not have complements or supplements. Okay? You cannot find an angle that's complementary to negative 10. It doesn't exist. Okay, so let's look at a few angles and just see if we can find the complement and the supplement. What makes the angle, what would you add to the angle to get 90? That's the complement. What would you add to the angle to get 180? That's the supplement. Okay, we'll start with 48 degrees. What's the complement, or what angle is complementary to 48 degrees? Yeah? 42. And anytime we are labeling an angle, we always have to put the symbol on it if it's degrees. If you leave the symbol off, that's 42 radians. Okay? So anytime you're doing something in degrees, make sure you put the circle. What about the supplement? What's the supplement of 48 degrees? Yeah? 132. Okay, how about negative 18? What's the complement? Yeah? There isn't one. Doesn't apply. What's the supplement? Yeah? There isn't one. No complement, no supplement. Okay, so there's going to be lots of questions in the homework that are quick, kind of simple like that. They're all very quick questions. Now, x degrees, we're going to assume that x is less than 90, because if x was bigger than 90, it wouldn't have a complement. So what's the complement of x degrees? Yep.
It would be 90 minus x.
Yep.
And then for the other one, it would be 180 minus x. All the degree is.
Again, assuming x is less than 90, because if x is more than 90, well, then you'd run into problems finding the complement. Any questions on that? Okay. All right, the last thing. So radians. It's another way we can measure angles. In higher math, it's the most common way. Degrees isn't really used. If you look at the word radians, does anyone see what that word kind of looks like? Yeah? Kind of looks like radius. Just take the A-N out and make it a U. Okay, it looks kind of like radius. And radians has a lot to do with a circle. And circles have a radius. Right, so I'm going to try to explain to you what a radian looks like. And then I'll explain what's the formula to change between radians and degrees. Okay, so what I've drawn in this diagram, this is called a central angle. It's a circle with an angle inside it, and the vertex of the angle is at the center. Two rays come out from the center, and they intercept, or they hit the edge of the circle at this point and that point. If you connect between A and B, tracing along the circumference of the circle, that's called an arc. So the notation for this would be arc AB. Arcs are not direction. They're not like rays. Rays, direction matters. You could call it arc AB or arc BA. It's the same thing. So any question on just what that diagram is? Okay. So the first thing I'm going to give you is it's kind of a visual. Okay? It's not a formula to convert between radians and degrees, but it's a way you can visualize what a radian would actually look like. The distance from here to here, segment CB, what is that called?
Radius.
That's the radius. How about distance from A to C?
Radius.
That's also the radius. Now, arc AB has a length as well. If you took like a piece of string and you measured the length of arc AB, and then you straightened it out, and it came out to exactly the same size as the radius, then what you would have here is a picture of 1 radian. So 1 radian on a circle looks like when the arc comes out to the exact length as the radius. And that doesn't have to happen, right? If you had a circle like this, and you drew an angle like that, there's your arc. In that case, is the arc the same length as the radius? No, it's a lot smaller. So this angle is a lot smaller than 1 radian. Likewise, if you had something like this, here's your initial side, here's your terminal side, and here's your arc. Does that arc look like it's the same size as the radius? No, it's a lot bigger. So that angle is a lot bigger than 1 radian. But if you draw it so that the length of this arc is equal to the length of the radius, then you've just drawn a picture of 1 radian. So that gives you kind of a visual. That's not perfect. I think that's a little big. Probably bring it in just a little bit. And that's about what 1 radian would look like. Okay, so any question on the visual, what it would look like? All right, so now the important thing is how do we convert between the radians and degrees? Well, I gotta start you with something, all right? You have to have some fact to start with to figure this out. So I'm going to give you a piece of information, and using that, we can build on it to figure out formulas to convert between radians and degrees. And the piece of information that I am going to give you has to do with what's called a unit circle. A unit circle is just a circle where the radius is 1. We're gonna do a whole unit on what's called unit circle trig. It's dealing with trigonometry on a circle that has a size of 1 unit for the radius. Now, on a unit circle, something special ends up happening. Let me show you what happens. Okay, it only happens on a circle where the size of the circle is 1 unit. So in a unit circle, if you draw an angle like that, and you measure it from here to here, if you measure the size of that angle, and then you take a piece of string, and you measure that length, the length of that arc and the measure of that angle will come out exactly the same. So if this angle is 4.9 radians, this would be 4.9, whatever unit you were using, inches. If this angle was 1.3 radians, then this arc would be 1.3 whatever, feet. Okay. These two numbers always come out exactly the same on a unit circle.
No, yeah, it's
Not a unit circle, that doesn't happen. Okay, but on a unit circle, it does. So knowing that, it's going to help us to figure out a connection between degrees and radians. So on a unit circle, if you measure the angle in radians, it comes out equal to the length of the arc. So if the arc is 5 inches, the angle is 5 radians. If the arc is 3.6 inches, the angle is 3.6 radians. They're always the same number. So let's think about how we could apply that to figure out a connection between degrees and radians. Because all I need is one connection. Like, for example, give me a connection between feet and inches. Yeah.
What 1 feet is 12 inches?
One foot
1 foot.
is 12 inches. Now that he told me that, I can figure out anything you want to know between feet and inches. You want to know how many inches in 6.4 feet? Well, 1 foot over 12 inches equals 6.4 feet over x inches. Cross multiply and I can figure it out. The key is that I needed to know something to start with. And that's what we need to figure out here. We need to know something to start with. Let's look back at the diagram. Let's see if we can find let's see if we can figure out how many radians in a full circle. Well, let's start with degrees. How many degrees in a full circle?
360.
360. So there are 360 degrees in a full circle. Now, we don't know how many radians are in a full circle. We haven't figured it out. So we don't know how many radians are in a full circle. But what could I measure in this circle that would be the same thing as the number of radians in a full circle? There's something else I can measure that would come out the same. Yeah?
The circumference.
The circumference, exactly. We said that the length of this and the measure of that are always the same. So if you can tell me the circumference of that circle, that's exactly the same as how many radians are in the full circle. So how do you find the circumference of a circle? Yeah? Yeah, circumference is 2 pi r. And specifically, we're dealing with a circle that has a radius of what?
1.
1. So what's 2 pi times 1?
2 pi.
2 pi. So the circumference of that circle is 2 pi. Well, let's go back down. The arc that we're doing this time is an arc that's so big, we're calling it the circumference. So the length of the circumference is equal to the angle in radians. Well, the length of our circumference is 2 pi. So that's equal to the angle that goes all the way around the circle. So how many radians to go all the way around the circle?
2 pi.
Exactly, 2 pi. So there are 2 pi radians in 360 degrees. That's also called a revolution. I don't think I said that, but one time around the circle is a revolution. So if I know that 2 pi radians is 360 degrees, what could I do on each side to simplify that a little bit? Yep. I could divide both sides by 2. Okay, that's better. In pi radians is 180 degrees. But think about when you give someone a conversion. And someone did it earlier, right here. When you give someone a conversion between two things, what number do you usually put in the conversion to
1.
make it easy? Usually you tell the person a 1, right? In 1 this, there's that many that. You don't tell someone in 4 feet there's 48 inches. You just say 1 foot, 12 inches. It's simple. So what I want to do here is get a 1 on one side. Which side do I want to do first? Okay. Let's get a 1 on the right side. How would you get a 1 on the right side? Yep.
Divide by 180.
Divide by 180. Not 180 degrees, not 180 radians, just the number 180. So here, what's 180 degrees divided by 180? Yeah? 1 degree equals pi over 180 radians. So there's a formula that tells you exactly what 1 degree is equal to. Now, let's say that I wanted a formula, for 2 degrees. What could I do to each side of this equation, which is true, to make it say 2 degrees equals, and then I have something I could figure out? Yeah?
For it to be equal, you need to do both sides, so you multiply both sides by 2.
Yeah. If you multiply both sides by 2, now it says 2 degrees equals. What if I wanted a formula for 5 degrees? What could I do on both sides?
Multiply them both by 5.
Multiply by 5. It's not what you're multiplying by in black. It's this part that's important in red. If you want to take degrees and convert it to radians, you take what you're trying to convert and you multiply it by pi, and then you divide it by 180. Those are the 2 steps to convert degrees to radians. You take what you want to convert and you times it by pi, and then you divide it by 180. And when we times it by pi, we're always going to use the pi symbol, not 3.14. And that's how you notice on here, a lot of the answers were left as pi over 2. Okay? So unless they tell us to round, you don't round. Leave the pi in your answer.
And you could use like the inverse to find degrees from radians.
Yes, to do it the other way, instead of multiplying by pi, you divide by pi.
And then multiply.
And you multiply by 180. Yep, you just reverse it. Yep. Now it can be easy to mix these up. Like multiply by pi, divide by pi, which one was it? Well, there's an easy way I can help you to remember it. All you have to do is, when I say degrees, I want you to think of the number 180. I want you to kind of connect those 2 things in your head. Connect the idea of degrees with the number 180. Connect the idea of radians with pi. So when I say radians, I want you to think pi symbol. Degrees, think 180. If you can remember that, then all of this becomes automatic. Okay, now I'll show you 1 or 2 converting each way. Okay, let's try this. So convert to radians. Anytime you're converting between radians and degrees, it's either pi over 180 or 180 over pi. It's always one of those 2. Think of it like this. 30 degrees. If you made it a fraction, what would it be?
30 over 1.
You just make it 30 over 1. Where is degrees in this fraction right now?
In the top.
It's in the top. You want it to disappear, so we end up with radians. If it's in the top here, where would you want it here to cancel out? Yep. You'd want it in the bottom. And when you think degrees, what number did I always say to think of with degrees? 180. So the 180 goes in the bottom. So that means what's going to go in the top? Pi, right? It is pi radians, but radians is something you would never put a label on. You just write pi. You don't put RAD. Now, degrees cancels. And how many times does 30 go into itself?
Once.
And into 180? 6. So what are we left with for a numerator and denominator?
Pi over 6.
Pi over 6. And if you look at what happens when you go to 30 degrees, it's exactly what it says, pi over 6. Okay, so that's one converting. We'll do one more. How about this one? I want to convert to radians. So where do you want degrees to go? Yep.
Pi over 180.
Degrees in the bottom, so it cancels out.
Yep.
Put the 180 in the bottom, put the pi in the top, and if you reduce that as much as you can, what do you get? Yep.
You get pi over 4.
Yep. Pi over 4. Okay. Now let's try. Well, actually, let me mention this. If they say they wanted a decimal here, then all you have to do is press the pi button and divide by 4. That's all you have to do to change it to a decimal. If they want a decimal, they'll tell you. Okay. How about this one? If you want to convert that to degrees, imagine it says RAD right next to the word pi. Where's radians going to go in this fraction? Yeah.
It would go on the bottom.
Goes in the bottom. And what number do we always think of when we think radians?
Pi.
Pi, which means what goes in the top?
180
180
degrees.
degrees. Pi's gone. And 2 goes into 180 how many times? 90. So 3 pi over 2 would be what in degrees? 270 degrees. Yep. Let's finish up with this one. Okay. Where that's radians. Pretend like it says radians right there. Where's radians going to go to cancel out? In the bottom.
Bottom.
And what number do we always put with radians?
Pi.
Pi. That means 180 goes in the top.
60 times 2.
3 goes into 180 how many times?
1. It goes in 60.
And what's 2 times 60 degrees?
120.
120.
Your weight.
And that's how you convert between degrees and radians.
So that's 120 degrees and how many radians?
2 pi over 3 radians. So like 2/3 of a radian is 120 degrees. Well, no, I shouldn't say it that way. 2 pi over 3 radians is 120 degrees. Okay, so on the board, that's the homework for tonight.
25.